Welcome back, everyone. Welcome back, everyone. We hope you had an insightful journey over the past 2 days. You are now watching the day 3 of the EPSILON 2026, and we are moving into a highly anticipated final segment. I am Bhumi Beloshe, the design head of the IEEE SIS GST.
On the topic Future Sensors for Earth Observation, Trends, Challenges, and Innovations.
Over the past few years, Earth observation technology have evolved rapidly, from advanced hyperspectral systems to innovative SAR capabilities and AI-powered data analytics. To explore what lies ahead, the opportunities, challenges, and innovations shaping the future, we have invited an incredible panel of expertise from across the globe.
Let's meet our distinguished panelists. First, we have with us Mr. Hayes Vanden Doll, an independent researcher specializing in Earth observation and geospatial data science. His work focuses on translating advances in satellite sensors into scalable and reliable insights, particularly in the face of challenges related to data volume and uncertainty. He also works with AstraTerra as a senior geospatial data scientist and board advisor.
We also have pleased to welcome Ms. Maria Luna, a doctoral student in the agriculture science. Her research focus on using hyperspectral and LiDAR remote sensing data to estimate biomass productivity in the Canadian grasslands.
We are also delighted to have Mr. Daniel Iran, who works at SATCO, a London-based startup providing high-resolution thermal imaging from its upcoming satellite constellation. He is part of the imagery team responsible for calibration and geofencing, or satellite data, with previous experience in flood prediction and astronomical data processing.
Joining us, Ms. Selina Satish Kumar, a geospatial analyst at Bone Bomitra specialization in satellites-based carbon monitoring and MRV system. She develops automated Earth observation workflows using Sentinel-2 SAR and data for soil carbon modeling, biomass estimates, and land use monitoring. Moderating today's discussion, we have Professor Madhuri Kulkarni, Assistant Professor in ECS Department as SIS Graduate School of Technology with 13 years of the teaching experience. She holds an master's degree in electronics and is currently pursuing PhD. A warm welcome to all the panelists and our moderator. We are thrilled to have such a diverse and accomplished group of experts with us today.
The stage is now set for an engaging and forward-looking discussion on next-generation Earth observation sensors, the role of AI and machine learning in remote sensing, challenges in managing data accuracy and volume, and emerging innovations in hyperspectral and SAR technologies.
We will also explore career and research opportunities in geoscience and remote sensing for aspiring professionals. With that, I will now like to hand over the panel discussion to our moderator, Professor Madhuri Kulkarni ma'am.
Thank you, Ishita, and thank you, Bhumi. Good evening, everyone. Good evening, everyone. It is a pleasure to welcome you all to today's panel discussion. So, thank you for taking the time to join us. We truly appreciate your presence and participation. I also warmly welcome all our esteemed panelists, Mr. Hayes, Mr. Daniel, Ms. Selena, and Ms. Maria. So, it is truly a privilege to moderate today's panel discussion on future sensors for Earth observation, challenges and innovations, recent trends related to that. So It's exciting to see such enthusiastic participation in a field that is shaping the future of our planet. So, as we are aware of the remote sensing and Earth observation have become indispensable tool in understanding our planet. Satellites continuously monitor our Earth, observing climate patterns, tracking natural disasters, analyzing land use changes, managing agricultural productivity, and supporting environmental protection efforts. So, through this discussion, we aim to explore not only the technical advancements in this field, but also the career pathways, research trends, skill requirements, and the future directions. So, with that, let us begin our discussion by first understanding the foundation of this domain. So, related to that, I would like to ask very first question to Ms. Daniel that we are now at a point where the satellites can monitor every corner of our planet and AI can analyze that data at unpredicted speed and scale. So before we go deeper and for the deeper related to that domain, for the benefit of the students and new learners in the academy, could you help us step back and understand this field more broadly? What exactly are the Earth observation and remote sensing? How do they work in simple terms, and why have they become so central to addressing the global challenges? Over to Mr. Daniel.
Hello, and thank you for having me today. So remote sensing is the technique of making measurements of something, a system, an object, without being in contact with it. So measuring the height of terrain without being on that terrain, measuring the temperature of the sea without having a thermometer in the sea, checking whether crops are drying out without being in the field and checking the plants directly. And then Earth observation is specifically that applied to the Earth. Remote sensing can generically apply to other planets as well, but Earth observation, specifically the Earth. The terms are quite interchangeable. It's either term in the satellite imaging community. It's very common to use either term. It can also include aerial imaging as well, where aerial imaging will generally give you better detail than you can get from a satellite as you are closer to the target. But a challenge with aerial imaging is you need to be able to fly over your target, which, if you're looking at the middle of the Pacific, for example, is quite challenging. Or if you're looking at an area which is far from where you are. Earth observation sensors tend to be in one of two categories. So there is passive, which is like a camera, really. You're looking at something, you're observing signals which you're already receiving, or you can be active. So radar or SAR is a common technique where you're sending out a signal and receiving something back. So the passive sensors, often, a lot of them are in the optical or the near infrared, observing light. You can also go then out into the thermal infrared or microwave as you get more specialized. You can even go as far as measuring gravitational force. There are some missions doing that. For active sensors, as I mentioned, often radar, but there are some LiDAR sensors, so sending out light signals and receiving those back, mostly for terrain measurement and for atmospheric analysis. And what sensor you use and what band you work in depends on what you want to measure. The orbits of the satellite are also important. So a low Earth orbit satellite will be closer to the Earth, but can't observe very much at once. Whereas a geostationary satellite, you can often observe much of the Earth at once. In terms of why is this a growing area, you mentioned a couple of the items yourself. You get global coverage, which is very useful. You can look anywhere in the world. You're not limited to what resources you're able to do to send out surveys yourself. There's an increasingly long history of remotely sensed data. There are decades worth of archival data. So if you're looking for analysis of how change has occurred over decades, that is possible. And the technique, the sensors we have, you're getting more advanced sensors, new types of sensors. There's an increasing amount. Every year there is something new out there with increased quality as well. And you also mentioned the computational power and the computational techniques, which again are growing. These data sets are very large, they are complex, decades worth of measurements of every week the Earth. It's a lot of data to work with. It's not possible to do that manually. And so we have been developing techniques for how do we analyze such large amounts of data. The computational capabilities we have been growing as well. So yeah, the amount of data we have, how the types of data we have, and how we can process that data have all meant we can answer more and more questions and answer those in more detail. And that has really pushed the growth of the field in the last few years.
Yes, thank you. Thank you for breaking that down so clearly. It's fascinating to see how a technology that started with simply capturing the images from the space has evolved into the sophisticated decision support system for the planet. Now that we have this broader understanding, let us explore for how emerging technologies, particularly AI, can reshaping. So, as we are aware of that, the field evolves. One of the biggest challenge we are seeing in the exploration of sensor options and data sources. A single environmental problem can now be addressed using the multiple types of the sensors. We are having the different types of the sensors comes under the remote sensing domain, such as multispectral, hyperspectral, SAR, thermal, LIDAR. So often all available for the same application. So related to that, let me ask the next question to Mr. Hayes. When we are designing a monitoring system today, how do you decide which sensor to be used? Is the choice driven primarily by the scientific question, the required spatial or temporal resolution, budget constraints, or something else? Could you share a concrete example where you had to make this decision and how you approached it? Over to you, sir.
Yeah, first of all, thank you for having me. It's a pleasure to be on this panel. It's a very interesting question, which actually comes back to the thing, like Daniel was saying, we are observing things. So if you want to set up an early warning system or a warning system in general, we have to first decide what it is that we want to detect or measure or monitor over time. And that will drive actually the decision which sensor to use, because not all sensors are applicable for a certain phenomena that you want to track over time. And if you take a concrete example, for example, we can look at early warning for flooding, and to see the effects of flooding over time, we could look at the combination of an SAR imaging, where we can see a change in reflectivity or actually backscatter of the radar signal, in combination to the optical image, where we see changes in soil moisture or water content, where different bandwidths are being absorbed more than before, before and after the flooding. So it's a very difficult question to answer without having first specified what you want to observe. A good example for this exercise is actually what is happening currently with Common Space. That's a humanitarian initiative to fly their open source satellites. And they're actually in the same exercise to define what it is that the community needs to address what matters most to them. So they are kind of in that exercise of scoping which satellites they would like to deploy in their constellation. And what they have seen by interviewing different stakeholders in the industry is that it matters not so much for the daily reacquisition. So like Daniel was saying, different satellites fly at different heights. Different heights means that you can revisit quicker or slower. And the amount of satellites that you have also depends on if you can have a daily revisit or even a monthly revisit, just depending on the density of your constellation. And what was seen in the stakeholder analysis is that for humanitarian aid, it matters at the event that you will have very high resolution. So they're going to a centimeter resolution on the ground. But to see change over time, it doesn't really matter that you have that high precision. Then you can go to a much coarser resolution. So then you're in the sweet spot of 1 to 5 meter resolution on the ground. And that kind of directs the sensor that you would deploy at that particular time. So that's not a real question on what sensor do we need. It is more coming from the other direction. What is it that you want to observe that will direct the sensor? If that makes sense.
Thank you, sir. That insightful perception. So moving towards the next question. So remote sensing data is unique in that it is often high-dimensional, multi-sensor, and collected over a time, which creates both opportunities and challenges. So to get the stage for the students and newcomers, I would like to ask about the core AI and machine learning tools that are driving this transformation. So my next question to Ms. Maria, what are the most commonly used AI and machine learning techniques in remote sensing today? And why are they particularly suitable for the satellite data?
Well, thank you very much for having me today as well. So to start answering these questions, there are many machine learning techniques and AI techniques that we can use in remote sensing today. So from my experience, I will say random forest is one of the most common for research, particularly leading through digital agriculture, because it enables of decision trees, handle high dimensional data, and also it works well with the small to medium training data sets, especially if we have big data sets in the case of hyperspectral data. Cellular imagery often has many spectral bands, so for multispectral or hyperspectral data. So random forest can handle correlated bands, so run variable importance as well, and modern nonlinear relationships. For example, vegetation indices like NDVI or NDWI versus biomass productivity, as we were discussing. So this technique performs well in land cover classification, biomass estimation, which is the research I'm mostly working right now, and soil property prediction. Also, in many studies, random forest is often the baseline model because it is accurate and very interpretable. Another technique that is very common nowadays, and I'm being pretty much hearing from other researchers, is the support vector machines. And this technique is very effective in high dimensional spaces because it works well within a limited training samples. So this is very suitable for satellite data, as remote sensing datasets often have many features, as you know, bands or channels, indices, or texture, for example, soil texture that may vary across the landscape. Other fewer label ground truth samples, and is very common because it uses different types of crop mapping in the case of digital agriculture as well, urban versus vegetation discrimination, and land cover classification. And also another very common and probably is, well, less common compared to the other ones, but is very interesting that I'm also want to explore a little bit in detail is the transformer-based model. So why this is growing very rapidly nowadays, because this technique handles long range of spatial and temporal dependencies and is very powerful for large scale Earth observation data sets. Also, is very suitable because satellite data characteristics include large spatial coverage, so more like from a small scale, more to larger field scale, and long temporal records, and multi-sensor integration. So for optical, a lot of you guys have mentioned SAR and LiDAR data sets as well. This technique also performs at a multimodal fusion, as well as a spatial temporal modeling. And this is still emerging, but increasingly being used at a global scale mapping for different types of research and disciplines for Earth observation particularly. Yeah.
Apart from that, we are using the NV and other Earth engine, Google Earth engine also for the processing of the hyperspectral data sets. Would you comment on that? Is any other panelist also? Envy is one of the tool which can be used for pre-processing.
Yeah. So for pre-processing, in the case of my research, I've been working with many, data sets with hyperspectral imaging that has been, we have tons of data. So it requires a lot of challenges for start working with the processing of each of the bands. So I've been using a lot of methods to subset that data set. For example, the principal component analysis is one of them that basically allow us to reduce the amount of bands, to look at specific channels and look at the productivity of biomass distribution. Also, it depends on the research that you are working with, on the type of discipline or what you try to accomplish as an objective. I'll say pre-processing requires a different type of workflow starting depending on the sensor you are using as well. In my case, I'm been using the high spec sensor, which is sensor that captures certain amount of imaging and a specific pixel scale. So processing requires a big workflow to accomplish the final hypercube on our end.
Yeah, maybe to add to that, I think it's also increasingly common that you mentioned there, Madhuri, so sort of pre-packaged tool sets. So MV, I mean, you could equally say, ARC and QGIS and so on. I think it's also increasingly common as these analyses get more complicated. We mentioned a lot of the deep learning there, to be using Python or languages like that to be building your own solutions. So that's, I think, actually increasingly common to be, for doing these more advanced automated analyses, to be building your own analysis, maybe obviously using existing libraries, existing techniques, but to be doing this more advanced analysis, to be working on it through coding and that, which of course many of these tools that you mentioned do have support for working with that. And it's useful to combine all of these techniques to be visualizing your data as well as processing it.
Yeah, to kind of contribute to that line of thought, I think I mentioned the connection was a little bit disturbed, but you mentioned Google Earth Engine as one of the platforms, and I think that's in the direction where that they see often or see more and more happening, that the large data sets are being made available in ingestible formats, like in Google Earth Engine, that you can connect to that computational platform. Other data sources are, for example, connecting to the Amazon Web Store as an S3 bucket, where other producers of data are storing their data, and that then can be brought into your own cloud computing environment. Like Daniel was saying, there are those packages that can quite efficiently handle the data to derive your own insights, and that's another aspect. And then you're using the front end or the graphical interfaces like in QGIS and an S3 ArcMap Pro to visualize that on your desktop or in the cloud where you want to process further. So I think with modern computation being not longer a bottleneck, there are different paths that you can take to do your analysis.
And also, I think Google Earth Engine, the involvement of Google Earth Engine has transformed how we even procure data in the first place. So priorly, we would have a lot of like cloud cover and things that we have to analyze before we get into our extraction of images. And now, because of when we Google for Good and Google Earth Engine being an integral part of how we handle data and cloud cover and other things, I think it has changed predominantly on how we see the ready to like use data sets. So I think there's a lot of evolution after we have seen the involvement of Google Earth Engine into the field of remote sensing, particularly.
Yeah, and that is also being picked up by other organizations. I would like to mention here the Food and Agricultural Organization, FAO, and their platform CEPAL, which actually plugs into Google Earth Engine as the computational engine, but then uses their own cloud computing shell to run pre-computed scripts and pipelines to, for example, detect disturbances in forest cover or calculate biomass. So that's another development that you see, that organizations are making those techniques available.
Thank you very much, all of you, sharing all the different aspects, tools which can be used to process this huge amount of hyperspectral remote sensing data. Thanks a lot. So moving towards our next question, to again Mr. Hayes. There is a significant hype around universal Earth observation foundation models. However, the technical reality is shifting towards using embedding, transforming multi-source datasets into numerical profile in which similar environmental conditions share a higher similarity scores. As we see a diversification of these products from Google's Alpha Earth to Teresa or Clay, do you envision a future where we consolidate into one supermodel, or will we see a fragmented landscape where, such like the different LLMs, each model gives a distinct answer based on its specific embedding profile?
That's a very difficult question to answer in 5 minutes, but I will try to be as concise as possible. So for students listening in and unfamiliar with the term an embedding model, like Maria was saying, we have different techniques to analyze data. There are different optical data sets available. So what happened in a foundation model is that the raw images are being converted into data vectors, where each pixel represents a set of numbers coming from the raw information that is being fed in. So for example, Landsat Sentinel-1 and 2 for a clay model. Teresa is using only Sentinel-1 and 2 in their learning process. And Google Earth and Google Alpha Earth is using any kind of data because it is a multimodal model. So that makes it a very complex model to decipher, and that's where their embeddings consist of a vector of 64 individual numbers. That is in global data sets then available for now 9 years. I think it runs from 2017 up to now, where every year is a slice in time and space. So will an embedding model convert into a physical model? I think we first have to look at the embeddings themselves, that are actually snapshots or summaries, yearly summaries. For now, they might go to a higher temporal resolution, but it will be very complex to do in terms of data availability. Even if there is a lot of data available, we have still to convert to a stable vector in that space to make the comparisons between one location and another location. So what similarity here means is that if I have a beach in New York, how similar is this beach to a beach in Normandy, France? Do I see differences, and where are those differences? And that's what the power of an embedding model is, that you can start comparing locations based on their fingerprint on the vector. Going to a physical model of the world, then we try to include physical processes to our observation, and that is an extra computational step, an extra modeling step, and I don't think that we are ready for that yet. There are initiatives to enhance the embeddings with a physical notion, but that is research that is just starting, and I think then we have to give it another 3 to 5 years to really see if it is feasible. And then coming back to the question, will there be only one? I think from where I'm looking at it, that would be very hard to get one model that governs all physical Earth processes, because there is too much diversity. So I more see it happening in the same sense as we see digital twins being developed for a certain area or a certain domain, so being very specific, and then not being transferable over different areas, or being very generic and be transferable, but then you're losing your depth of the data that you can, or the insights that you can derive from those models. So that's where I see the future heading towards the transition from an embedded model to a physical model.
Thank you, sir. Thanks a lot. So moving towards our next part of the discussion. So we have talked about the potential of AI in the remote sensing, but applying the AI to the satellite data is not always straightforward. It is somewhat different from the normal data processing. So satellite imagery is complex, high-dimensional, multi-temporal, and often noisy. So AI models face the unique challenges in the real-world use. So related to that, I would like to ask my next question to again Miss Maria. What are the biggest challenges in applying the AI and ML techniques to remote sensing data, such as data quality, generalization, and computational cost, and how can they be addressed?
Yeah, again, this is a very interesting question that probably a lot of us have, experience from our work. But also one of the biggest challenges in applying AI or machine learning to remote sensing data could be the data quality and the processing challenges. Remote sensing data, as you know, is rarely clean. So creep problems may include atmospheric effects. So for example, clouds or aerosol distort reflectant values, sensor noise, specifically in hyperspectral imagery, because they have the banding effect, calibration drift, and etc. As you may experience with the work you are looking at. Also, geometric misalignment, and this can be between sensors. So as you mentioned, Sentinel-2, LiDAR data, or if we are working with digital elevation models to look at the terrain of the surface of the site, and limited ground truth data. So for example, field data is very expensive and especially sparse, as you may realize this. Some solutions to address these challenges are atmospheric correction, so something that I've been working towards, so I know how this can be very challenging to accomplish. Radiometric normalization across dates. So if we're collecting biomass samples and we, try to do drone surveys through every month, so we need to specify the days that we're collecting the data. So for radiometric normalization across those days will be very essential in order to achieve all the goals here. Cloud masking for quality assurance and quality control bands, data harmonization between sensors. And we also need to be careful for field sampling design. So we need to pick what is the right sampling design for the goal we try to achieve. So stratified sampling, random sampling, using transect or a grid sampling. Our noise reduction. So as I mentioned previously, principal component analysis is one suitable technique for band reduction. Smoothing filters when we're working with hyperspectral imaging as well. And lastly, quality control of ground truth. As for computational cost, satellite data sets, as you know, are very massive. So for some examples can be Sentinel-2, as I mentioned previously, and many of us have worked probably in the past with these data sets, which normally is 10 to 20 meters resolution, time series across the years, national and continental coverage, and hyperspectral data because they have hundreds or even thousands of bands of channels. Some of the challenges for these could be the storage limitations, long time training. So it will take some time to train these specific data sets, especially if we're new users. GPU, which stands for graphic processing units, requirements for deep learning, and memory issues with hyperspectral cubes because of the extremely high computational demand that we may experience, especially nowadays.
Yes. So is any other panelist can comment on this? Apart from this, is any challenges to be faced by the new researchers for handling such high dimensional data?
So I mean, I think the point Maria made at the end there around dealing with the size of the data sets is increasingly one of, it is not something you can, if you're doing a more advanced analysis, anything other than a few images, you can't do it on your own laptop or computer. You can't do it all at once on a server. So what are the computational methods? How can you compute, work through a data set in a way where you can do it? It is, if I was doing, say, an analysis over the entirety of India, I can't load my images across India all at once. But there is no computational system available where I can do that. I need to split up my problem. That's often the technique. You have to split up your problem. Maybe it's making it into smaller areas, doing it at each time step differently. But how do you tackle that is really quite an important problem to understand. There's techniques out there. Tools like Google Earth Engine have support for how can you tackle these problems, but understanding those is quite important for anyone coming into the field.
And also, Maria explained on how we harmonize different data sets or different like resolutions, for a matter of fact. So for me, when we work at SOC modeling, like carbon modeling, we have to like procure data from different data sets, and some cases we have to downscale them. And in sometimes we lose data in that process. We lose data on how major it affects that place when we consider like soil texture, for a matter of fact. So I think when we downscale or even upscale for that matter, we lose and kind of like expand the pixel. So I think that also comes into consideration when we have to work with harmonized data.
Yeah, and to add on that, I think the ground truthing is very important as well. And that's kind of an aspect that is often overlooked. So you can do an analysis, you can do any kind of spectral analysis, like calculating an NDVI or an water moisture content, or if you go out of the spectral imaging, you could do a climate model to see what is the precipitation. And those models, they need something to be verified against. And that's the item that is missed most in any project that I am involved in, is how do you get this accurate ground truth data. So that's why running a global model, you can do it, but then your sample set will be global, so your ground truthing will be global. So that means that the site comparisons will be very hard, because not all locations will react the same to the same analysis. So how do you make sure that your sample set that you have collected is appropriate for the analysis that you are doing?
Yes, that's correct. That to handle this large amount of data, few challenges to be faced by our new researchers in this domain. That one of the challenges is the pre-processing. So we should do the radiometric, geometric corrections before using this data for our application. Apart from this, due to the high dimensional data set, we require the more computational power. Computational cost is more. So it's correct. So thanks very much for your valuable inputs. So moving towards our next question to Mr. Daniel. Now we have discussed the current AI techniques and challenges can be faced. So let us look ahead. AI and remote sensing are evolving rapidly, and the new research directions are emerging every year. So what are the most exciting emerging research areas at the intersection of AI and remote sensing that students should be aware of that? What are the different skill sets students should have to focus to build strong foundation in the AI-based remote sensing?
Yeah. So of course, AI is an interesting term. It's a very wide term. Recently, it's come along recently, often with the arrival of large language models. In my experience, the LLMs themselves have not had a massive impact on how we analyze the data. They've certainly made it easier to understand how to do the analyses, helping people get these done. Although one area I have seen them come up is data discovery or data query problems. So I've seen people working towards, you have a question like, find me images of all of the steel mills in India. And then having an LLM which is able to understand that question, go and find out the spectral signature of that and then return that data? Since it's a challenging question to often find these sorts of these data sets. Is this image mostly grassy or not? These are questions we have, and we have the tools to answer, but they are often challenging to work with. So I've seen some people working towards that. I think that's still quite an active area of research. It's still very recently coming out. We've mentioned deep learning. That is still really where most of the AI in remote sensing is. Deep learning is a very wide area. There's many different techniques, new ones come along, but equally, I think a lot of what is currently being done is still how do we best apply these techniques as well. So we are still using, we've mentioned random forest, we've mentioned support vector machines, neural networks. These are still the most common techniques I see being applied to the data. But I guess we have moved beyond things like simple edge detection as the tool we use. That might be an input to this, but it is no longer just do a simple transformation of the data. It is using these deep learning models is certainly what's common. In terms of what we're then applying those towards, object or feature detection or image segmentation remain an important problem. They have been something that's focused on for a long time. There is still a long way to go, and whether that's because the detection is the answer you need, is there grass in this image or not, or often it's then what goes into the next step of your processing. And related to that, change detection. So has something changed? So we've mentioned humanitarian use cases, for example, where you want to know after some disaster, where have changes occurred? How is agriculture changing over time? And there are still challenges with applying that to high resolution data, where shadow and other little effects, things tend to vary a lot more on smaller spatial scales. How do you do that without confusing your results? And how do you do change detection if you're combining these different missions that we've got? That's still a very active area. We mentioned foundation models. How do you combine different data sets or different spectral regimes is a very active problem that we haven't yet got solutions to, I think it's fair to say. Super resolution is one. So Selena mentioned upscaling and downscaling data. There's, no matter what data you have, you always want a little bit more resolution out of it. You want to go a bit further. So there's a lot of work of super resolution, so trying to find things which are at or below the resolution of the data. What can you see that's really hard to see in there? But then, as Heis mentioned, you generate a super resolution result. Can you validate it's telling you the truth? A lot of them, you take a higher resolution data set as your training and use the lower resolution data set and try and scale it up. But how do you know it's not just telling you the things that you've told it? Again, those are active research problems. And on the preparation side, again, we've mentioned making data available. So it's not perhaps so much research, but on the technical aspects of how do we make our data available for machines to work with, so that you don't have to go on a certain body's website, type into the search bar, download it, make it so that you can access these in a machine readable way. So there's been a lot of work on developing and implementing technical standards like stack catalogs, data formats like ZAR and cloud optimized GeoTIFF for making data better available for these sorts of analyses. You asked a bit about what sort of skills would you look for. I think an important change in the last few years is that simple data analysis is not something you do. You no longer employ someone to look at an image and find what's in it, or to mark out the field boundaries. So an important aspect, I'd say, for anyone new coming into the field is that you need the knowledge to build those automations. You are no longer doing this work. You need to work out how to make a computer to solve these problems. And I think we've hinted at this, of that then means you need a bit of a fundamental understanding of what are you doing. We've mentioned georeferencing. How do coordinate systems work? How do coordinate transformations work? How do you resample data? For data processing, we've mentioned that lots. So how do I deal with a very large data set? I'd say you will need some sort of programming expertise. Python is very common. There's other languages like R. It's a little, knowing one language, you can move to another. But Python is certainly, I think it's fair to say that's by far the most common. Everyone works in Python. For deep learning, understanding the basic concepts of deep learning. How do those work? How do neural networks work? What are random forests? Just the basic understanding of what are all these techniques? How do you implement them? As Heis mentioned, how do you train and validate models? How do you make sure they're doing what you want? Especially because in Earth observation, you rarely have a labeled training data set. You don't have the answer because you're trying to solve it. And it's such a vast data set. So how do you come around these problems? And then the base understanding of, we've mentioned, how do you choose your spectral bands? What missions do you go with? What data sets? And that's, you need an understanding of what are these observational techniques? What bands do what are useful, especially as we get into hyperspectral. There's so many bands there, and you need to choose. You need to know. And maybe do you have the understanding of which ones are important, or do you use other techniques to tell you which are important? We've mentioned a bit of that. And how these quite common data processing techniques, co-registering data sets, resampling data sets, denoising data sets. Again, understanding the basics of what these are, and then whatever problem you're on, you can then go and learn what's appropriate for each one.
Can I add something to what Daniel said? Is that okay if I can?
Yes, sure. Yes.
Yeah, so I would like to cover a lot of points, actually, especially when somebody is getting into remote sensing. It can be like quite overwhelming because a lot of data sets, a lot of techniques, a lot of a lot of things to focus on. So I think when you start out, you need to first focus on the purpose of it. Like, what are you going to get out of it? What is the outcome of it? What are they expecting from you? So I think when you have like a particular like a lineage of where you're heading towards to, and then it'd be easier for you to get the data sets, like the pre-processed ones. We have a lot of techniques that already like do so many things for us in the terms of data sets. You need to go and do from level 1. You can get level 2 data sets already. And seeing like for change detection or anything, it's just that you need to know. And data analysis, apart from data science, even data analysis also quite important skill set that anyone that needs to acquire when they're getting into remote sensing or trying to translate data into useful information currently.
Yeah, and if I may add here another kind of point of view, is that we are in this discussion kind of constantly switching between the terms Earth observation and remote sensing. And I would like to introduce, or I would like here to say or emphasize that Earth observation is actually the umbrella on which remote sensing falls, as it is one of the techniques that are useful. So if you're thinking about Earth observation, then how to combine those things would be a very good skill set to have as well. To have knowledge of the adjacent fields to your main domain. For example, if I would like to use remote sensing for algae detection, then it would be good to know what kind of spectral imaging I would require for detecting algae in water. But it would also be interesting to know a little bit about how surface waters are being monitored, and can we create that monitoring system combining the surface water level measurements on a high resolution monitoring system on the ground to the remote sensing, to get that kind of linkage between what is happening on the ground and what can I observe from space. And then you can try to extrapolate to that other areas where you won't have that modeling ground station model network to feed into your pipeline of that you have created there, the machine learning pipeline or a deep learning pipeline, to do the analysis of what does that change detection actually mean to the values that I see. So domain awareness is something that I would bring in here as well.
Yes, that's correct. The domain awareness should be there, and then only we can able to apply the AI techniques over that based upon our requirement. What is our objective? What type of the applications we have chosen? Based upon that, we should able to apply the different AI techniques. Thanks very much for all the panelists. So, moving towards our next question, as we explored the power of AI in the Earth observation, it's also essential to address the responsibilities that come with it. So, AI driven satellite monitoring can offer incredible benefits, but it also raises important ethical concerns, especially around the privacy, bias, and surveillance. So, my next question to Ms. Selina, what ethical considerations should we keep in mind while using AI in the Earth observation, especially in terms of the privacy, bias, and the surveillance?
Well, that's actually a very technical question from my perspective. So, first of all, when we use satellite data, it appears anonymous to us, like high resolution, and monitoring also can be like a little bit overwhelming on what we're trying to do. So sometimes it can like abbreviate or breach, how do I say, land ownership or agriculture for infrastructure at that point. So when we see and how we're going to use it, first we need to see who are we going to give this data to, or how we're going to utilize this data for. And I want to add a different perspective to it in terms of like ethical use. On a project that I worked for was based on illegal mine detection in Amazon. So we used like these mining areas were quite illegal, and they were not supposed to have these mining points in that area. So remote sensing was quite handy for us to detect these illegal areas and make analysis on how these forests are being deteriorated. So I think that's one perspective of how we can put good use of Earth observation and remote sensing in that matter. And in terms of bias, especially when we work with when we work with modeling or like training data sets for that matter. So when we train data sets, it eventually has some sort of bias. Like in particular one area, it might not effectively function in the other area. Let's say you train a model with soil texture or climate zones for Africa, it may not necessarily work for India or other aspects. So that would in turn give us like mild errors or major errors for a matter of fact. I think we need to have like clear idea of different climate zones, of different particular testing areas that we're working on, and also train them on based on that. That can be of one particular idea that we could delve onto. And the third thing that maybe is that I would like, it could be transparency, especially when we are working in carbon modeling or like offsetting carbon. Transparency may not be an ideal terminology that companies use or even like researchers would use. So I think when we have AI-based Earth observation systems, I think we should start influencing how we treat the environment and be more transparent with our data sets or with our results to see how we're actually impacting the ecosystem or the environment for the matter of fact. Yeah, that's it for me.
Thank you, Selena. So the next question is open to all. While doing the fusion techniques, so is any technical challenges while doing the fusion of the different sensors data for a particular application? Is any challenges can be faced?
So the matching your data. So often when you want to process your data, you want to have your data on a set of pixels, which are all co-registered and samples. If you are combining different missions, you will very rarely have that. We will have different pixel sizes. They will be offset from one another. So combining those, the resampling and the co-registration we've mentioned. And co-registration, what I'm mentioning there is that these data are mapped to the ground. They are not perfectly mapped. It is a challenge. There may be some offset between the different data sets you're combining. And a couple of pixels offset can be a very significant problem in, say, change detection. these pixels will appear to have changed between these measurements. So working with that, understanding how to do that. And maybe moving a little away from some of the agency missions, which tend to be more surveyed. They're always looking at quite the same angles. If you're using data from other missions, you may be looking from different angles of the ground. So, quite 45, 50 degree angles from vertical. So you're looking at the sides of buildings, or you're looking at the sides of hills, and you can't see behind them. You're looking from the wrong angle. How do you deal with that if you're combining different sensors? And that's a challenging problem. There are many techniques. Sometimes that is what you want to do. You want to be looking from different angles to build up a 3D image, but that can be a challenge with combining different sensors, different missions which operate very differently. I think SAR missions, for example, very often are looking, it's off nadir would be the term here, looking to the side and all that, pointing at a target, not constantly surveying underneath them. And that is, dealing with that, understanding what is going on when trying to combine these different data sets is certainly very important. And Selena is mentioning, you can get more highly processed data sets, but has that processing before done something which makes the fusion of different missions difficult? Have they done something? And that's often the case of when you're doing a specific problem, read the guide, read the documentation, understand. But being aware that if you're doing different data fusion, they can be collected with very different methods, and maybe those have an effect on different impacts on what you're observing. The same feature can look very different for reasons you didn't expect.
Yes, thank you, sir. So, Miss Maria, I would like to ask that do you want to share some experience related to your research work? You are working on the hyperspectral and LiDAR images, sensor data to estimate the biomass productivity. So, do you want to share any experience that will be beneficial for our new researchers if who want to use these types of the areas?
Yeah, I've been learning from each of you very interesting, topics on the area that will be actually beneficial for my research, like mentioning through, data visualization, and even how, like, using all this coding through Python are something that I've been using. And right now I'm working through my data analysis for hyperspectral imaging, and it's been a challenge because of the amount of data that we collect. And since I went to the field, I did monthly drone surveys during the growing season. So that makes even a little bit more challenging to kind of standardize all the data at once. So it would be good to know, like, explore the data in depth and see which appropriate method can be applied to handle all this amount of data. Something that I've been working right now is try to reduce noise, and also the try to have all the channels reduced by the pitch of the bands, and see which bands are more suitable for biomass prediction, and bring through the biomass, and see which vegetation indices are correlated with it. So something that I've been experiencing is challenging if it's the right method that I should be using, or maybe it's another method that could be more beneficial to that. So I'm looking at what are the methods that are more suitable for data reduction for hyperspectral imaging. As you know, there is a lot of bands that we need to handle with. And it's something I've been thinking about this. Yes, maybe Daniel was mentioning using different packages that would help us kind of manage the data, because data management is very important on how we want to accomplish those results, right? Specifically, we have a lot of hypercubes. It will help us to kind of visualize better on what we want to accomplish in my end. So from my research is being certainly challenges I've been facing, but at the same time, I know what I want to accomplish. So my ultimate goal will be to upscaling from more to a smaller, finer scale to a very larger scale, or even like a larger scale in terms of a regional scale. So that will help me to see how biomass prediction will vary in different, regions in the province that I'm living right now, which is Manitoba, is one of the provinces that agriculture is mostly one of the economic resources here. So this will also potentially will benefit for cattle productivity and the other type of agricultural applications in the region. So from my experience, I'll say that I'm still working towards. So it's a lot of interesting, results that I'm getting in terms of biomass productivity, but at the same time, I'm stubborn thinking, is this the right method? If I'm getting good results, should I keep going with it or explore other methods that will be, beneficial for subsequent analysis in particular? So yeah, I learned a lot today because I gained more knowledge on, using Python, maybe switching from R to Python or using other packages that will maybe help me to handle the data in a better way.
Thanks, Maria, for sharing your experience. That will be definitely beneficial for the new researchers. So, as we near the end of our discussion, it's important to look ahead. We have covered current technologies, applications, and challenges can be faced in this particular area. So, now let us focus on what the next decade could be. So, related to that, the next question I would like to ask to Ms. Selena that what do you see as the future of AI in the remote sensing over the next 5 to 10 years?
Over the next 10-15 years, I think AI in remote sensing would probably like move in four directions. So instead of like having like image analyses with static imagery, we would have it like more dynamic, more real time, instead of like environmental intelligence. So we'll be having like self-explanatory. It would have models that would probably say what we're doing, why we're doing, in real time, instead of having it to pre-process and things like that. That would be one direction that we would be focusing. And secondly, I think the embedding based approaches will become more common. I feel I think all of us, Maria, Daniel, and everyone else, was saying how we kind of like fuse and make ensemble like different ML or different like approaches could be fused into one to get to a final conclusion. I think that will be more explored in the future. And also, I think remote sensing and AI would not only be focusing on like environmental or particularly Earth observation. I think it would delve into many other fields as well. Maybe in healthcare, not directly into healthcare, but like in vast or like branches of healthcare. Maybe like some things that I could think of is like maybe detection of microplastics that have like direct link to our health. I think that could be one application that could grow into more in the future, and also the involvement of multi-sensors. Like I said, instead of having just one set of imagery like optical or thermal, we can incorporate all the available data sets to have more detailed insights and to get more clear ideas of what's happening with our environment. So these are the few things that I can think of.
Yes, that's correct. That though we are having the hyperspectral data, we can extract the huge amount of data as compared to the normal image data. So we are getting the multiple bands information within that. But apart from this, the certain challenges can be faced while handling such a huge amount of data, such as the unavailability of the labeled data set. We can say that limited ground truth data is available. So certain pre-processing to be done on this data so that we can extract the correct information and then we can use for our application. So let us come towards the end of the discussion. So let me thank all our panelists for the insightful discussion. Today we explored how Earth observations has evolved from simple satellite imagining into a powerful AI-driven system that can monitor our planet in the real time, support critical decisions, and address global challenges like climate change, agriculture, and disaster responses. We also learned that the future of this field lies not just in more data, but in the smarter integration, combining multiple sensors, advanced analytics, and ethical responsible AI. For students and young professionals, the key takeaway is that this is a highly interdisciplinary domain where the technical skill, scientific understanding, and the ethical awareness all are matters. As we move forward, the biggest opportunities will come to those who can bridge these worlds, bridging together remote sensing, AI, and the real world impacts. So, thank you all for joining us. And we hope this discussion inspires you to explore the next generation of Earth observation. Okay, so thank you very much, all the panelists, for sharing their knowledge. That will be definitely benefits for all the audience which are here. So now the forum is open for the question answering. Participants, you can post your questions in chat so that our panelists can answer.
So, would you like us to take the questions as they come up? So we've got the first one there. So, in terms of future sensors for climate policy, what I have seen from people working in this field is that one of the very important things has actually been not so much future, but the very long-term time series. So one of the problems they are dealing with is that for climate analysis, having a very long time series to prove, to detect the changes in the environment is vitally important. And understanding, getting that down to as good an accuracy and precision as we can is very important. So what they are working on for future sensors, for future missions, is firstly making them more accurate, making them better at doing these measurements, but also making sure that those sensors are incredibly well calibrated to match previous measurements or to remain consistent with previous measurements. So we mentioned the bias in data sets. So this is one of the very, very important problems. Or they don't want to be saying the Earth is getting warmer because our sensors are drifting relative to each other. And making sure that doesn't occur has been very important. Improved resolution, both in time and space, I think is very important to doing these things. Having this better data, better temporal coverage is still something they need improved measurements of. So there are many missions now where we are not looking at launching a single satellite. They're wanting to launch a fleet of satellites to get much better coverage of the Earth, and that has also been pushing into it and understanding, not just focusing on a single time of day, but different times of day as well. So that's some of the direction I've seen in the climate monitoring space. Often a lot of it is we know what we want to measure already. I think we've got good at it. We just have to stay and make sure we're remaining very good at it. And these are very carefully calibrated missions.
Thank you, sir. So, Maria, you are having one question. So, from a researcher perspective, what current limitations exist in remote sensing sensors that researchers are actively trying to overcome?
Yeah, that's a very, very interesting question. Again, back through my experience, I've been facing challenges such as like the sensor setup. Even sometimes when we are in the field and we try to fly the drone, and then we normally use a base station for that. And then when we try to kind of bring it to the lab and see all how the data looks and is possibly not in the right currency system, we need to make a lot of corrections in that. So switching from technology, we need to follow our specific workflow through analyze all those images. So by doing that, we need to know, are we doing the right, following the right procedure to accomplish this? Sometimes we face challenges by, analyzing all this data, and it needs to pass through quality assurance and control. And this is also a challenge because if we don't know exactly what we want to do to standardize all the data at once, it may bring problems for the subsequent analysis. So from my perspective, using one sensor and then bring another sensor that in terms of I'm collecting data with hyperspectral at the same time with LiDAR, and we try to do data fusion, we need to standardize that. But now the question is how we're going to do that. So in terms of methodology, we're going to see, is data fusion going to help us to bring all these methods to be, correlate with the results we try to accomplish. So this is one of the challenges that probably a lot of students could face when working with different type of sensors at once, no? And see what is the main primary objective you want to see to accomplish this. Sometimes it's not what you're looking for, but you try to come up with a question that probably you see, I have answer for this. So this is one you need to set up a good guide, a good questionnaire, and see what is correct and what is no, why is not giving me its results. So working with different type of sensors is going to be a little challenging if you don't know how to fuse the data properly. So that hope that answer the question.
Yes, Mr. Mary. Thank you. One more question.
Yeah.
For student interest, yes.
Yeah, there's a question on the screen. I think for open source tools to hyperspectral imaging, there are several solutions to take here. So there are already in ArcGIS or ArcGIS Pro and in QGIS packages to analyze the data, because the data will come in, like Maria was saying, I think, that there are data cubes. So data cubes can be visualized. If you want to interrogate them, then you will have to go to a programming pipeline. And there are Python packages that can do. One of them is, for example, I put it in I can't post directly, but it is the Spectral Pi, or SPI. That has a long history of working with this type of data. And yeah, that are solutions that you can find. So are there any particular that I would recommend? No, because it is how you want to operate with the data depends on the kind of hyperspectral data that you are working with. If you're asking a general package to work with, then the one I just mentioned is a good one. And otherwise, the kind of the NetCDF format, because that's where it would come into, would give you a native entry point to do your own analysis.
Yes, thank you. Just check. Is any another question? For students interested in GIS and remote sensing, what foundational skills that most important to build early? That already we have discussed. I think anyone add on that same question? Anyone wants to add?
It's, I think, a very hard question to answer without having the background of the student. For me, coming into the Earth observation scene, having a strong environmental science background helps me to understand what I want to do with Earth observation and remote sensing. So, like I said earlier in the discussion, having that domain knowledge and start from your domain knowledge and then see how Earth observation could help address the problems that you see in your field is, I think, a very, very good way to get into. And then it doesn't really matter too much on which program path you take. You will have to do some programming if you are more comfortable in R, because that was the package that you were trained in, and you can continue on R. If addressing the numerical solution is better in Python, then you can go to the Python solution. Both are currently well supported in the industry, so I wouldn't say that's really a main skill set. I think the openness of being able to pick up on the conversation that is happening in the field and being that intermediary in the domain is I think the soft skill that I would train on.
Yeah, just to add to that, I think I'd agree strongly. Of in terms of technical skills, I think the data analysis is key, but that isn't geospatial or Earth observation specific data analysis. How do you analyze data? And as Heis mentioned, many of us have come from different backgrounds into Earth observation, and Earth observation is a tool really to help us do other things. Earth observation isn't the answer. It's not where we're trying to get to. We're trying to answer other questions. The other thing I would say is that ability to learn and discover, to be able to go out and learn how do you solve these problems, what has been done before, how are these sensors working. I mentioned earlier a lot of different areas, but a lot of that is being aware of these different parts of the problem and then being able to go and learn and understand how to deal with those as and when they become important, because every one of the areas that we're working in is different. We all focus on different problems, but we understand enough of the little basics to know, I don't know enough here, I need to learn more, or I need to find an expert. So having that is, I think, perhaps the most important thing, because you can't know everything. That's impossible.
Yes, that's correct. So thank you very much, all the panelists, for sharing their knowledge. So I would like to hand over to our host. Yes, Bhumi and Ishita.
That was truly an insightful and inspiring discussion, from emerging sensor technologies to AI-driven analytics and future research pathways. We are sure our audience has gained valuable perspective.
We have now come to the end of our final session under the GRSS track. I would like to sincerely thank all the panelists for sharing their expertise and insights with us today.
We would also like to extend a virtual token of gratitude to Mr. Hayes for sharing his valuable insights with us. Your guidance has truly added depth to our learning expertise. Next, we would like to extend a virtual token of gratitude to Maria. We are deeply grateful for your support and for the warmth you brought to this session. Your insights have left a lasting impact on all of us. Next, we would also like to extend a virtual token of gratitude to Mr. Daniel Evans. We sincerely appreciate your time and expertise. Your perspectives and thoughtful contributions have enriched today's discussion immensely. Lastly, we would like to thank Selena ma'am for your gracious presence and for inspiring us with your knowledge and experience. It has been an honor to have you all with us. And our moderator, Madhuri ma'am. A special note of thanks to our moderator for seamlessly guiding the session and ensuring such an engaging and meaningful discussion.
Thank you for being a part of EPSILON 2026 and for helping us understand the future trends, challenges, and innovations in the Earth observation technology.